Hello friends, today we will learn about biomolecules interaction. First of all, van der Waals law. Van der Waals reaction, electrostatic, hydrophobic interactions. Like this, all interactions we will know in this video. Van der Waals laws. When two uncharged atoms are brought very close together, their surrounding electron clouds influence each other. Random variations in the positions of the electrons around one nucleus may create a transient electric dipole, which includes a transient opposite electric dipole in the nearby atom. The two dipoles weakly attract each other, bringing the two nuclei closer. These weak attractions are called van der Waals interactions. As the two nuclei draw closer together, their electron clouds begin to repel each other. At the point where the van der Waals attraction exactly balances this repulsive force, the nuclei are said to be in van der Waals contact. Let's know about electrostatic force. An electrostatic interaction depends on the electric charges on atoms. The energy of an electrostatic interaction is given by Coulomb's law, that is E equals to kq1 q2 by dr, where E is the energy, q1 and q2 are the charges on the two atoms, and r is the distance between the two atoms, in atoms normally denoted in angstroms, and d is the dielectric constant, and k is the proportionality constant. Interactions between charged groups shape biomolecular structure. Electrostatic interactions between oppositely charged groups within or between biomolecules are termed salt bridges. Salt bridges are comparable in strength to hydrogen bonds but act over larger distances. They thus often facilitate the binding of charged molecule and ions to proteins and nucleic acids. Fixed positive and negative charges attract each other strongly. Consider a carboxylate ion in contact with NH3 plus and or with an ion of calcium. From the van der Waals law, van der Waals radii, the ionic crystal radius of Ca2 plus of 0.10 nm, we can estimate an approximate distance between the centers of positive and negative charge of 0.25 nm in both cases. It is of interest to apply Coulomb's law to compute the force F between two charged particles which are almost in contact. Electrostatic forces are of great significance in interactions between molecules and in the induction of charged in conformations of molecules. For example, attraction between COO minus and NH3 plus groups can occur in interactions between proteins. Calcium ions often interact with carboxylate groups. The doubly charged Ca2 plus bringing between the two carboxylate or other polar groups. This occurs in carbohydrates such as agarose, converting solutions of these molecules into rigid gels. Individual macromolecules as well as cell surfaces usually carry a net negative charge at neutral pH. This causes the surface to repel each other. However, at a certain distance of separation, the van der Waals attractive forces will balance the electrostatic repulsion. Now come to hydrogen bonding. Let's know about hydrogen bonding. CHE of the most important weak interactions between biological important molecules is the hydrogen bond. These bonds are the result of electrostatic attraction caused by the uneven distribution of electrons within covalent bonds. A hydrogen bond is formed when the positively charged end of the dipoles is attracted to the negative end of another dipole. Water molecules tend to hydrogen bond. Hydrogen bond strongly one to another. Each oxygen atom can be hydrogen bonded to two other molecules and each hydrogen to another water molecule. Thus, every water molecule can have up to 4 hydrogen bonded neighbors. The strength of hydrogen bonds as measured by the bond energy varies over the range 10 to 40 kJ per mole. The stronger the hydrogen bond, the shorter its length. Hydrogen bonds are strongest when the hydrogen atom and the two heavy atoms to which it is bonded are in a straight line. For this reason, hydrogen bonds tend to be linear. However, the dipoles forming the hydrogen bond do not have to be collinear for strong hydrogen bonding. Let's know about hydrophobic interaction. Fats, hydrocarbons and other materials whose molecules consist largely of nonpolar groups have a low solubility in water and a high solubility in nonpolar solvents. Similarly, the long alkyl groups of fatty acid esters aggregate within membranes and nonpolar side chains of proteins are often packed together in the centers of protein molecules. Because it is as if the nonpolar groups fear water, this is known as the hydrophobic effect. The terms hydrophobic forces, hydrophobic interactions and hydrophobic bonding have also been used. However, the latter term can be misleading because the hydrophobic effect arises not out of any special attraction between nonpolar groups but primarily from the strong internal cohesion of the hydrogen bonded water structure. When two hydrophobic groups come together to form a hydrophobic bond, water molecules are freed from the structured region around the hydrophobic surfaces and the entropy increases. Various efforts have been made to develop scales of hydrophobicity that can be used to predict the probability of finding a given amino acid side chain buried within a protein or in a surface facing water. Thank you.